also Mr. Fikri, the doctor co-student from ITE, and also student from IPS, Ivan. Okay. Also, good morning for student from masuk course degree in Pajajaran University today. We are very glad to have a lecture. This is our second lecture from Dr. Isawa Tanabe. He's an expert of, especially for muon and computational science. So now he's the senior researcher in the Kenisina Center for Acceleration-Based Science, and also he's become a professor in Hokkaido University, and yes, a professor from in University of Indonesia. Okay. I think the student is already here. We have now we have 30 participants. So I think you have Dr. Watanabe. You have enough time to discuss a lot of things. Okay, our student will be very happy to have your lecture. So, okay. Okay, Watanabe-san, time is short.
Okay, thank you very much for introducing me again. Okay, morning everybody. Let's start again my second talk. I share my screen. So, can you see my screen?
Yes, yes.
Okay, let's start. So, the last time what I talk about is what is a MUSR, how we can use the particle muons for the material science. So then today, I again have 2 hours to talk about the DFT, that is the computational research on the material science by using muons. So then, but I'm not a computational guy. I'm not a theoretician. So then I'm an experimentalist. So then I cannot talk about the detail, the example, and also the research of the DFT calculations. So if you're interested in the detailed thing, just like a programming, computing something, of course I can talk with all of you. But if you are interested in you have much more specialists around you in Indonesia, in DP, the UI and Parapo and Defense University. So could you please talk to them directly? That is much more easier for all of you. So then what I'm going to talk is it's not like a normal theory talk. Then I aim how we use a DFT with in conjunction with the experimental results. So that means why the experimentalist is planning to use a DFT. How we understand the experimental result, then how we can proceed much more deeper understanding with the DFT calculations. That point I'd like to appeal in my talk. So in order to do, in the beginning of my talk, I will talk about again some experimental results which cannot be talked in my last talk. Then I introduce what is the problem from the experimental results. Then what sort of things we need to think about by using DFT. So if you can understand just such kind of flow, why we need to do the computational efforts to understand the experimental result, that is quite nice. I'm very happy to spend my time to talk about my research. Okay, so now the first slide is just like recurrent immunity facility, which I showed you already in the last talk. Then I again recall your memory. What we are doing at this facility is 2 types of the research. One is the experimental method, the another one the computational method. The experimental one is muon spin relaxation measurement, and the computational one is density functional theory calculations. So mu spin, the mu SAR, can be done at regional mu facility. That means outside Japan, but density functional theory calculation, we say simply DFT, can be done in Japan. But sometimes you can do this research even from Indonesia. Actually, some of my old students are now still doing this research from Indonesia. Then, in the end, I talk about density function theory calculations. So this is just to recall your memory, how to do the MSR. So I simply summarize. We throw in mu into the sample, and detecting the signal from the sample, we measure this kind of the MSR, the time spectrum. This is the basic information to discuss electric state of materials. Then how to analyze this time spectrum? Of course, we can use the analysis function to fit this time spectrum. But from this result, how deeply we can discuss the electric state, that is the different point, completely different. So how much we are now doing the MSR research on other materials. These are just like images of our target materials. The main targets are the magnetic materials, this one magnetic materials, and superconducting materials. And recently, we are using MSR for the organic molecules and biomaterials, and not so many, but some researchers are doing the industrial application, just like battery materials or car materials. But main job is on the superconductivity and magnetism. So then I'm now working on the magnetism and superconductivity. So that today, my talk is very related to superconductivity. So then in order to introduce my DFT studies on the superconductivity, I simply explain about the superconductivity. What is this and how we can understand the history of superconductivity. And what sort of things we can discuss from superconductivity, MSR studies of superconductivity is just like this. From now on, I will talk about simply how the superconductivity is formed. So in this case, we have to discuss the pairing symmetry of the Cooper pair. Maybe you studied the name of the Cooper pair when you are in a master course from Professor Risdi. So, and also penetration depth. These two parameters are basic parameters to discuss the superconducting state. But luckily, MSR can give us the very important information on those parameters. For instance, this is the example to show the triplet superconductivity in the world. So this was given from MSR. And also penetration depth. This is one example to measure the penetration depth by MSR from the surface to the inside of the sample of the high TC superconducting cuprate. This is also very interesting because the penetration depth can be directly measured by using MSR, but it's not so easy for other techniques to measure this kind of penetration depth directly. So this is a very strong advantage of the MSR to study superconducting state. So then once new superconductors appear, what we do is just catch up samples and do the MSR and discuss these kind of very important parameters very quickly. So then I talk about some example how we applied the MSR to other materials. This one is my collaborators study to discuss the coexisting state of the magnetic state of superconductivity in iron superconducting oxide. So this was just done within 5 days and published in Nature Materials in the beginning of the story history of this iron superconductor. This was also the very shocking data. Then on the basis of this data, other researchers they were carrying on their own studies to discuss the superconducting state. This is another example of my old paper. This one is also how the superconducting state is destroyed by doping the non-magnetic impurity. This time, I just start to talk with the Professor Risdi. He was in the doctoral course student. He was a doctoral course student in the Tohoku University, under the supervised by the Professor Koike. Then Professor Koike was my biggest collaborator for a long time. Then on the basis of the collaboration, we gave the first data to show the suppression and enhancement of superconducting state by doping the non-magnetic impurities. And also this one is also very interesting, the frustrated material. So this one is a good example to sense by muons, to sense the lattice vibration by the muons. So lattice vibration is not so easy to sense even by using other experimental techniques, but we can then sense sort of the lattice vibration by using muons, because muon is a very fine tool to discuss the very small changes in the magnetic state. For instance, this is a temperature dependence of the lattice vibration motion. So there are two modes, the one mode, low temperature mode, high temperature mode. So this one is a first report to show such kind of two modes of the lattice vibration in the magnetic materials, but still this is in the non-magnetic state. But molybdenum has magnetic materials and magnetic interaction. Then due to the fluctuations, there are two kinds of lattice vibrations. This one is also recent, the data done by the Indonesian student. She is in the ETS now and working as a staff member of the physics department. So this one, the pyrocloth system, she measured the fine change of the magnetic order state in some sort of the pyrocloth iridates. So this one is also the very new data to show the fine change of the magnetic state of the pyrocloth iridates. So published in the PRB. And also former student also published this data in a PRB as well. So what I want to say is mu is a very fine, the fine magnetic probe to sense a small magnetic state. Then we can apply the MUSR to many the materials, which can be difficult to be studied by other experimental techniques. This is also another example to sense a very small magnetic moment, the zeroite. We can dope the electrons in the zeroite cages. This is zeroite-like, but zeroite is very familiar, the materials for all of us. Sometimes we can have zeroites in the toothpaste. Every morning, we use this kind of zeroites to brush our tooth. So then if we dope the electrons into this kind of the zeroite cage inside, we can see the very tiny order state by using MUSR. This is also the first report to show the appearance of this kind of the very small magnetic moment in a zeroite. This is a wonderful Nature paper by using the MUSR. So MUSR also can sense the small kind, very small kind of the single state magnetic order state. Then this one is to discuss what is the original, the mechanism origin, what is the origin of what is spin and liquid state. How the both condensation is appeared and forms the spin liquid state. This one is the first paper to discuss the flow MUSR. So then this one still survived even after 10 years of this publication. This is still referred and discussed in a wide range of the research, the collaborations. So this one is also Jack's paper. They are done by their team member for a very short time. Mu is a very powerful tool to sense a magnetic order. So then I spent only 13 hours to get this data and can make one publication. So such a kind of quick measurement is also good. And to sense a magnetic order state is also very good. It's very easy for MUSR. So please remember, this kind of temperature dependence or time spectrum is a key to be applied for the DFT. How we can understand how much the deep information we can have from this kind of time spectrum by using a DFT. That is the motivation why we started to use a DFT. And also, this is also another example to show the nanographene. Recently, the graphene seed is very important to be studied from viewpoint of the industrial applications. So this is a part of such kind of study. So this is not a one seed graphene. This is a multi-seed, the nanographenes. So the MUSR can also be applied to the nanoscience. Then the MU can sense the new state of the electric, new electric state inside the nanomaterials. So I'm going to talk about in the end, I'm going to talk about one example, how we can apply the DFT to discuss the MESR on such kind of this kind of graphene materials. So these are just only simple examples, how we can apply the MESR to materials. Then in the past, we've got many achievement from MESR experiments. Then we can discuss the many kind of new state. However, on the experiment, has the limitation to discuss how much the information we can discuss. The experiment itself has the very big limitations. Then how to break such a limitation is we need other techniques. For instance, how we can discuss a spin structure from MESR. Fundamentally we can do by using MESR, but honestly speaking, we cannot discuss such kind of spin structure just like a neutron so easily. Then lots of people said in order to discuss spin structure, we should do neutron, the scattering experiment. However, the neutron scattering experiment, sometimes we need a large single crystal, so not so easy to discuss, to carry out. Instead, MESR can do this kind of measurement even using a small amount powder samples. Then if we can have the way to discuss spin structure, we can expand our research areas much more rather than neutron science. In addition, the hyperfine interaction. This is very important to discuss the local interaction and also local electric state in the materials around the magnetic moment. But at this moment, hyperfine interaction is not so easy to discuss from MESR only. Then what sort of things we need to discuss? That is, again, the computational efforts we need. So the how, that is the question. Then lots of people are starting to think about the DFT calculations. So please remember, please be aware, I'm not talking about the DFT. So recently, very many people, many MESR researchers are talking about the DFT. Everywhere DFT. However, this stream to use the DFT is not so old. So then maybe just last 10 years, we start to talk about the DFT because if we proceed the DFT calculations, we find how big computing resources are needed for our DFT purposes. So then we can say DFT, but people are very limited to do at this moment. Luckily, Reckon has a very nice supercomputing system. Then I can finally do the DFT calculations. So okay, so as I talked to you, the MESR itself has a limitation to discuss electric state. So what is the fundamental problem MESR is? We can throw in the muon into the material, but we don't know where is muon. Where muon is sitting, how muon is sitting, and in time it's changing or not changing, the stable sitting, the sensing, the magnetic moment, we are not so sure. We don't know how muon is sensing the surrounding electric state and how muon is existing in the material. That also the other problem. Honestly speaking, we don't know. From the experiment, the efforts, it's not so easy to understand such kind of the muon state inside the material. Then for instance, we throw in muons, but in the material, there is the electric magnetic moment. So how to sense the dynamic or static properties of this electric magnetic moment is a key of the study of the physics, especially very recently for high TC and other advanced materials, how the electric magnetic moment is behaving in time and how this is stable in time. That is very, very important, the parameters and knowledge to discuss the origin of the materials. However, we don't know where is muon. For instance, if muon is sitting very far away from the magnetic moment, the magnetic interaction between muons and magnetic moment is very big, as you know. Yeah, you can image this one. If you put the magnet, okay, just simple magnet, very far away, how magnets are interacting? Almost nothing. On the other hand, if a muon is sitting near the electron, the magnetic interaction becomes much bigger. Then we can sense the electromagnetic moment by using muon. For instance, if there are two muon sites, our information from USR can be mixed. On the other hand, if the muon is all the time too far from the electrons, even though we do the MUSR, we have nothing. Then we have to give up. So then, in order to discuss this kind of magnetic interaction, we have to understand we have to understand where is muon. So the information of the muon position is a key, especially the key for the future of the MUSR. But at this moment, we don't know how to determine the muon positions inside the material. Then some researchers are now developing how to understand the positions. But as we proceed these kind of DFT research, the problems becomes severer and harder and complicated. That is at this moment the question how much we can exactly understand where is muon. Then I'm now continuing the DFT studies nearly 10 years. So first people, the Budikun, he's in the UNPAD now, doing some still sort of calculations. And second one, the Aina from the Malaysia, Aina-san, Akin-san, and the Indonesia, Ramadan-kun, Irwan-kun, and recently from Thailand, the young people joined for a short time to complete some kind of the DFT researches, but still not yet completed. Then we need more students at this moment. Lucky, one student can join to us from this October, so then I can proceed more researches. So then where we are calculating and what is our activity, and where is our activity is ongoing is, we say Hokusai, because Hokusai is just like a name of the painter in around 200 years ago in Japan. This is a very famous, the Hokusai painting, Hokusai picture. So, and also worldwide famous, this picture. So I don't know why the Riken give this name to the supercomputing system. So this is a picture of using the supercomputing system in Riken, made by Fujitsu. So not so big, but a very powerful system compared to any other recent supercomputing system in the world. And for instance, I think you know about the number one supercomputing system, Riken K, named K. About 5 years ago, this was the fastest supercomputing machine in the world. Then they kept their position for 2 years, but now it's not number one, and also destroyed already and thrown away. Then we downgraded this K supercomputing system and put in a Hokusai. So basically, the quality of the computing speed of the Hokusai is same with K, 1 petaflop. So that means 5 years after the K appeared, we can use the quality, of K within the Riken. Then we are now enjoying our DFT calculation by using Hokusai. So now the number one is Fugaku. Fugaku is just after K, sitting in the same position. So in the Kobe, the Riken facility. So this one is at this moment number one supercomputing system in the world. Unfortunately, this is a kind of the national project, so it's not so easy for us to use Fugaku directly because programming is very complicated and performance should be very, very too heavy for us. Then there was a competition in Japan how we can use Fugaku. So the competition is too hard. Sometimes the competition, our suggested computing the program has to be along with the national strategy. Then luckily we got a chance to be the Fugaku last month. Then we visited Fugaku. So then this year the Fugaku view. This is very big system, but this is just an parallel computing system. Then this one is just like as a one machine. So then if you have a chance to count the Riken, we can go Kobe again, then to see the Fugaku. So this is just like a view of the visit to the Hokusai. So this is not so big compared to Fugaku, and not so many bodies are there, but still the performance is quite nice. Then he's just like I can say the people of this of the center, which is in charge of the operation of the Hokusai. At this moment, Hokusai is working well. Then we can doing the calculations. So how good Hokusai is? This is a simple comparison between some of the computing facilities in Indonesia. So there are two systems in Hokusai: the Great Wave and the Big Wave. The Great Wave is has been already replaced to the next generation named the sailing ship. The performance becomes much more higher and bigger. Then the Big Wave is still working. This has much more bigger capacity compared to the sailing ship. So the Big Wave is going to be replaced in next year to be much more better one. So then if you can join, some of you would like to join to us, you can use much more better computing facilities for your Dft calculations. Then comparing to the normal PC, we are now using the 70,000 cores for our calculations. For instance, in normal PC, you have 12 cores, 24 cores, but if you pay much more money, maybe you can use 34 cores or 64 cores. I don't know exactly, but my student investigated the LIPI laboratory. They have 64 cores, and LIPI supercomputing state just only has around 1,000 cores. So then compared to this, we have more than 70 times the computing cores. Then we can do the much more bigger calculations, the quicker and better. Then we can do diffuse calculations. That means this is very important. After we investigated Dft programs, we found that we need this kind of supercomputing system. Just only normal PC is not so good enough. For instance, we are now using the commercial-based Dft calculation program named the BASP, the Vienna AV Ensure programming, the computing package. This can run, that sort of the package can run on a PC, but we cannot do any real calculations on a PC due to the limitation of these computing resources. Okay, so then what we are doing is the Dft calculation. What is Dft? This is just like an image of the Dft. There are many electrons in the material, of course. So then, but we don't know, we cannot understand how each electron is moving as all electrons are interacting one by one. This is completely impossible because there are many electrons, just like Avogadro numbers. We cannot calculate all the electron interactions, assuming each electrons. And from the quantum mechanics, we cannot judge each electron, where is it. So how we can understand electrons inside the material, then how we can discuss electrical state. So then Dft was suggested to understand this kind of difference. Then Dft, the concept of Dft is Dft is just density, okay, density. So then we think this kind of volume of electrons to be just like a density, okay. Other density. That means if there are many electrons there, for instance, around here, we put the large density here. But if the number of electrons is very dilute around here, we put the lower density around here. Then we have density distributions. Then how we can manage such kind of the density distributions, that is not impossible. Then by using a Schrödinger equation like this, we can calculate how these densities are interacting and changing time by time. So that is important. So then here, so I said just now here, dense density, dilute density. So if we have mesh here, like that, then if you can define each density on each mesh, then if the mesh number is much more many, if there are many mesh numbers, the density, the situation becomes very realistic. But for instance, if you have only 4 mesh, like that, the density here is only 1 density, 2 density, 4th density, 3rd density, 4th densities. So that means they're quite different from the real situation. We say resolution. So for instance, if you have the bad resolution or TV, you cannot see the good picture. But recently we say 4K, 8K TV, the machine, that has a much more higher resolution. So that means the resolution is very important to simulate the realistic electric state by using a DFT calculate in the DFT calculations. So then if the number of the mesh increases, what is important is the computing performance. So the large number of mesh means we need more calculations. That means we need more higher the performance of the computing resources. That is why just only simple PC is not working to discuss the DFT calculations. Then we need a supercomputing state. So yeah, what we are doing is very simple. Just specify the density and make a mesh, specify density and apply the interaction function among each mesh. Then they calculate self-consistently. Then takes time. Then we get the final result. So basically, not so difficult to say, but not so easy to carry out. So then these are the guys to suggest this kind of the concept. Then they've got a Nobel prize in the chemistry in 1998. So what we are doing is we assume the crystal structure, because the crystal structure like this is a very basic information for all of us. So as long as we don't know the crystal structure, we cannot discuss anything. Then crystal structure is first. Then we see the crystal structure so carefully, and they specify each atom. Where is each atom? This is just like an example how we can specify the crystal lattice. Then we calculate the potential, electrostatic potential. Electrostatic potential is what is that? Is, for instance, the atom has a plus charge. Okay, atom has a plus charge. Electrons around the atom have negative charge. As long as we have negative and positive charge, we can estimate the electrostatic potential. Then such kind of electrostatic potential is easily calculated from the unit cell. Then after we specify the crystal structure, what we do is to estimate the electrostatic potential. This is the first step to discuss the muon science. Then this arrow point is the local minimum, the low potential area inside this crystal structure. So as long as we have many meshes to cut off the one unit cell, this area of the local potential becomes much more smoother. This is important. So then that is why we are estimating local electrostatic potential is due to the muon's charge. I think I'm not so sure whether I talked about the muon charge in my last talk. Basically, the muon has the positive charge. Of course, there is another muon which has a negative charge, but we use the positive muon for material science, basically material science. Then positive charge likes negative charge. Positive charge doesn't like the positive charge. That means muon doesn't like to close to the atomic position. But muon would like to come closer to the electron's area, which has a higher density. Its electron has a higher density, for instance, around here. Muon would like to come to such a kind of area. On the other hand, if there is less electron density, for instance, around here, muon doesn't want to come to here rather than this area. So this is a very basic point from the viewpoint of the electric interaction. Then we need to know about the potential first. So then the potential means where muon would like to come. So this is one example, okay? So then yellow part is just like a local minimum potential. Local minimum means a low potential area, not position. Of course, we can specify the positions if it has many meshes. This point is a minimum position or something. Just in order to draw the area, just we set up a little bit wider the local potential like this. So then, for instance, this red point, you can see, I think, this is a complete local minimum potential position. Then around this position, there is a sort of the potential area, for instance, like that. So M1, we say minimum 1, minimum is here to here, but the potential shape around the minimum position is kind of like this. Then we can say here is a minimum position, but in order to draw the area, for instance, if you specify like 100 milli eV from the bottom, like this area, so this one, this height of the potential becomes this arrow area. So that is why I'm not talking about area, is I talk later on, because this is due to the to think about the 0-point vibration motion of the muon itself. I will talk about later on. Okay. So then, but this is just like a two-dimensional, the local minimum potential. However, real material is not in two-dimensional. This one is in three-dimensional. Then we have to discuss in the three-dimensional condition. This is the example. Okay, can you see the black lines here? These are the mesh. These are meshes. How we can have, how much and how low resolution we have. Then this is a third, just like a third potential. Then the local minimum potential is around here. Then the potential is the expanding around the local minimum potential. So on the other hand, this one is much more. This has much more finer the resolution, that may find a smaller mesh compared to this. If so, you can simply count how many meshes are there. How many meshes are there? Even in the same the scheme, the number of meshes are completely different. So that means we have to, in this case, we can discuss interaction among these meshes. So not so many. But on the other hand, this one has many meshes. So the many the interactions we have to specify. Then this computing volume of this side becomes much more bigger and harder, even though we are discussing the completely same structure, completely same potential, the position. This is a key point why we need a supercomputing system. Please understand why we need a supercomputing system. For instance, if you do the same the calculation by using your PC, then if you want to have the result very quicker, this number of mesh becomes much more smaller. So then it becomes unrealistic. Then you need to buy more things. So after we specify the potential, we put the mu in here, then self-consistently we discuss, we calculate the electric state around the mu. So in the end, what we have is we have the information of the magnetic moment, like this and like this. So this one, the density of the magnetic moment. Magnetic moment means electronic magnetic moment. In some sense, this is just a kind of the map of the density of the electrons. This is also density of the magnetic moment. So here is a high density, here is less density. Then if you see carefully, the magnetic moment size becomes larger around here, even though the mesh is the same. So that means the high density here and low density around here. So if you say the local magnetic moment in materials, usually we put the magnetic moment just only one on the atom. But actually speaking, and honestly speaking, the real situation is completely different. In the case of real situation, what we can see is the magnetic moment is distributing, following the density, distribution density of electrons. So this is a kind of, just a high TC, the high TC case. Here's kappa here. So in order to discuss the magnetic moment, we usually put the magnetic moment on the kappa, because kappa 2 plus has one magnetic moment. However, this size of magnetic moment is distributing. For instance, this kappa is connecting together, bridging the oxygen here. Oxygen is a very non-magnetic material, non-magnetic atom. So then there must be no magnetic moment on the oxygen position. But if we calculate carefully by using the higher number of mesh, just like the high mesh number, we can see the distribution, appearance or distribution of the local spin density even on the oxygen position. This is the new finding from the DFT calculations. But 10 years ago, we cannot simulate this kind of the appearance of the very tiny magnetic moment, even from the DFT calculations. If we have the lower density mesh here, like 4 times, 5 times bigger, this small density becomes becomes zero because the average effect it becomes zero, so we cannot understand how the electrons is distributing around the copper and around this oxygen. But now we can do the much more finer calculations, and we can find out this kind of the local density distribution. Then we can find out how much magnetic moment appears on each the copper atom. So this one is in some sense final result over the research at this moment. So red mark here, this is the muon. So this is a very large cell size. We put a muon in one muon into here. The estimate is the local magnetic moment around the muon. So just near the muon, the local magnetic moment is changing. I talk about later on. And also at the oxygen position, we found the appearance of the local density, those spins, even at oxygen position. So then what we do is first we calculate the potential, then they decide the initial position of the muon. Muon is a prober. Then estimate the magnetic moment state, then match with the experimental result. This is our method at this moment. Then from the computational method, we can discuss the electric state, then how much the hyperfine interactions muon has, we can estimate. On the other hand, from the experimental viewpoint, we can see the real experimental data. That means how much exactly the internal field muon is watching. Then joining with the two research, then we discuss the top physics by using both of the research methods. So please understand that some people do the only computational method. I show the example later on. Some people do only mere experiments. However, recently, also the computational research and only mere experiment, that is also good. Then we can find out many things. However, in order to break through this kind of situation, what we have to do is we have to cover both. That means that in order to discuss a mere experiment, we need computational efforts. Then we need computational efforts to prove the mere experiment. So this is a recent stream of the muon science on the Earth. So please understand, not so many people can do this due to the limitation of the accessibility to the supercomputing system. At this moment, as long as I understand, who is progressing these studies is my team in Japan, and also the Oxford University team, and our team in Parma. But Parma's one is a little bit slow. And also in Britain, there are one university in the north, not McMaster, I just forget. The one very nice, the high-class researchers is also doing the similar, they're computing the calculations. I show you later on the examples. Okay, so this is just a concept why we need computational efforts. So until this position, do you have any questions? Does somebody have questions?
Okay, if you have question, raise your hand, or you can write in the chat box. Okay, I think from here. Oh, okay. Watanabe-san, I have one silly question. 2 weeks ago, you mentioned that we can get 3 types of data using a MUSR. One is Gaussian-like, then exponential, and the third one is a precision, something like in this slide. So for the computational physics, or if we want to calibrate the data using the computational technique, which data that we can calibrate for the computational one. I mean, is it, for example, Gaussian like behavior or exponential or precision like all the spectra uh, can be used for the calibration in computational science for the muon position, for example, or
Okay, so then at this moment, I'm now concentrating on the muon spin precession only at this moment.
okay, yeah, okay,
But we are now developing how to discuss the Gaussian-like and exponential-like. So that is the next stream in the world. They are not so easy, honestly speaking. So the easiest way is the easiest one is to discuss a muon spin precession motion first. Then there are lots of people are doing now. But next step is to discuss a Gaussian Lorentzian part. So I'm now developing it with some theoreticians. So we need much more theories so then to apply to the muon, the time spectrum. That is the next step.
okay.
So for instance, next week, I have a discussion with the University of Tokyo people how to develop the theory and equation to discuss this kind of the Gaussian or Lorentzian relaxation. That's the next step.
Okay.
Okay.
Okay, thank you.
Wait.
Yes.
So then, okay, I move to the next step. So now I talked about the little bit DFT confusing the things. I hope nobody is sleeping now at this moment. Unfortunately, on the Zoom meeting, I cannot see anybody. Then I don't know how many people are sleeping now. So maybe Lissikun can check how many are still awaking.
Problem.
So then now I talk about the superconductors because this is my specialty. How specialty? So then why we are now studying DFT with superconductors? Just simply I introduce. Before that, I introduced the superconducting characters. So in the beginning of the 20th century, just 100 years ago, what the top physics in the world is how the resistivity in a metal, it behaves at low temperatures. But nowadays, we know how behaves the resistivity in low temperatures. They are very easily in like a lecture or textbook. But 100 years ago, this was a top physics. Then how? But at this moment, at that time, they had no cryogen to cool down the sample below the nitrogen temperature. Then the Kamarin Onnes, he broke such kind the situation by using his technique. Kamarin Onnes is very famous. He is also Nobel winner. And why he is famous is he made this system. This is the worldwide first Helm liquefier. In the beginning of 20th centuries, we have the system to cool down the liquid helium to make the liquid helium. So Kamarin Onnes himself is not a physicist. He is just like an engineer. Then he think about how to realize how to make the liquid helium. So this was the model. This was in his old laboratory, Leiden University. Then luckily I visited there. Then I saw the real system, how to cool down the liquid helium. But this is his laboratory in Leiden University is now closed. And this system is displayed in the museum of the university. So then by using this, what he's got is liquid helium. And he succeeded to cool down the mercury first. Then he found the superconductivity. This was the first observation of superconducting state in the world. So that is why he chose the mercury is only one atom, the elements which show liquid state, even in that is metal liquid state at the room temperature. Then if they cool down the mercury, what's happened at the low temperature side? That was his just interest. Then he found superconductivity. The name of the superconductivity, but honestly speaking, we can see the zero resistance. The why he didn't say zero resistance resistivity is he couldn't believe the zero resistance 100 years ago. He has not so much knowledge. We know that superconductivity shows a complete zero resistance. However, he couldn't believe it. Then he said superconductivity. He didn't say zero conductivity. So then we are still using the word of superconductivity even after 100 years. This is the first, the observation of superconductivity. He was in some sense lucky guy because he just tried to liquefy the helium, then just simply cool down the mercury and measured resistivity, then got a Nobel Prize. So this was the old memory in his laboratory. So this professor is like a successor of the Kamaring Onnes laboratory, but he was the last professor of the Kamaring Onnes laboratory. Then he closed this laboratory and moved everything to the museum. This one is like lighting the names of the walls of the laboratory. Who visited to the Kamaring Onnes laboratory. Many people visited in the 100 years. In here, for instance, Max Born. You can see the Max Born, the Einstein here. So then the signature, by the many the world famous the researchers, we can see. This is also displayed in the Leiden University Museum. So if you have opportunity to go to Netherlands, so please visit to Leiden, and then see this real signatures on the wall. But nowadays, liquefier becomes like this, then we can use the liquefier as we like. Especially in Japan, in Reckon, the liquefied helium is available to discuss, to measure the many things. But unfortunately, in Indonesia, it's not so easy to get this cryogen. So then we need a collaboration. And if you bring the many good research teams and performance and also your passions, we can collaborate together to discuss new physics. So what the application of superconductivity is, the typical one is a linear motor car. So niobium-3 titanium is the typical superconducting wire to be used for just like this kind of linear motor car. This one a Japanese system, this one Chinese system. So both are using this niobium-3 the titanium, Tc 23 Kelvin, but still they need a liquid helium to cool down this wire to below to the Tc. But liquid helium is very expensive, not so easy to make, not so easy to handle. So then what is required is, are there any materials which has higher Tc than the nitrogen temperature, liquid nitrogen temperature? If we can have such kind of materials, the liquid nitrogen is easily used to cool down to achieve the superconducting state. Then the mechanism of superconductivity, simply speaking, is like that. So these are lattice, okay? The atomic position there, the atom has the plus charge. And if the electron comes in, then if the electron has interaction with the lattice, electron attracts and pull in the surrounding atoms to the electron side. This is due to the phonon interaction between this is the Coulomb interaction between the atomic charge and electron charge. So in this case, this atom would like to come back to the original position, even after these atoms are pulled into the electron side. In this case, if the another electron is very near to the first electron, so this electron is pulled by the returning atom like this. Then from outside, these two electrons seems to be coupling via just a motion of the atom. The motion of the atom we say phonon. So that means the phonon-mediated coupling we can see from outside. So two electrons seems to be coupling together via the phonon, the motion. So then these kind of two electrons are coupled state, we say Cooper pair. The Cooper pair is necessary to form the superconducting states in any cases. So this case, the Cooper pair is formed via phonon interaction. So this is a basic mechanism to realize the superconducting state. We say BCS theory. Bardeen, Cooper, Schrieffer suggested this model. Then they explained the superconducting state. Then they got a Nobel Prize. But recently, until recently, very recently, the TC material development was going well. Then the TC but didn't go ahead so well. The niobium-3, the germanium, the maximum is just like 23 Kelvin. We need liquid helium to realize the superconducting state. But very recently, there was a breakthrough. That is a high TC superconductivity. Then suddenly, the TC becomes much higher than liquid nitrogen temperature, which is 77 Kelvin. So then Bednotes and Mueller, they've got a Nobel Prize due to this observation of the high TC superconductivity. So then now the high TC superconductivity is still the fashionable area to study for the physicist. So then we can use the high TC Q plate for the industrial materials by using liquid nitrogen. The biggest problem is these are metal. Okay, what is the difference is the usual one is metal. However, high TC is ceramic, not so easy to bend, not so easy to deform. The metal is easy to bend. So then in order to make a wire by ceramic, we need a special technique. In the beginning of high TC history, the many companies try to synthesize the high TC cuprates, making a wire, but many companies are left because the difficulty to synthesize this kind of the wires by ceramic. But if we can do if we can make such kind of the wires by using high TC, that can be a complete breakthrough of the electric condition on the Earth. We can say. So this one is the how we can demonstrate the superconductivity by using high TC. This one a TV program. This one a high TC material. So if we go to a high TC material cuprate, we can demonstrate the superconducting state character by like this. Please see. So this high TC is cooled down by nitrogen temperature, liquid nitrogen. So this is just on a simple magnet. So this is a floating effect. So please see, magnet is floating from the high TC material. So then due to the superconducting state, magnet is floating from the high TC. This is how to operate the linear motor car. Linear motor car is using this character of superconducting state. And on the other hand, okay, I show one more interesting video. This one is made by the Professor Risley's laboratory long time ago. This is with a fishing effect. Okay, so we have a magnet here, the simple magnet here. Then this is high TC material. At room temperature, high TC is just only ceramic. It doesn't attach to the magnet. But once we cool down this high TC ceramic in a cup noodle, okay, cup noodle, pot noodle, by using liquid nitrogen like this, just simply cool down. Then the high TC cuprate is being cooled down. At the bottom, nothing at this moment, just outside, but magnet can be suspended, just like this. Magnet is a little bit far away from the bottom of the seafood cup noodle, but still floating. This is also fishing effect. Then we can do, this is just like a similar, the mechanism, why the linear motor car is floating. So this is also another character of the high TC cuprate. So then if we can make a high TC cuprate in a wire condition, then we can change our lifestyle in the world. So this is also like a dream of the researchers. However, not so easy to make this kind of wires. So the basic properties, this is very important from now. This is the basic crystal structure of the high TC cuprate. High TC cuprate is a ceramic and also has like a low dimensional structure. The we say two-dimensional structure. The seat here, two-dimensional seat here. Then the basic, there are many types of the high TC cuprates. However, the basic structure of two-dimensional seat is all the same. Bismuth system, and this one electron doped system. They all have the layer structure. This is very important and key to realize the high temperature superconducting state. So then we insert the coupled plane. This is also the key, how to discard the superconducting state. We cannot forget about this coupled plane. Then this coupled plane is inserted into the blocking layer. in here. Blocking layer is insulating. Then this coupled plane can keep the two-dimensionality. This is a key. So this is very common, the feature of the high TC superconducting state. Then we need to discuss electric state of this coupled plane, especially for kappa. So then our target for Dft calculation runs onto the astrometry couple 4. This is a much more simpler material among the high TC family. And also there are many studies who are built up in the past. Then we can discuss our result referencing with other built up the existing data. So then we chose this. Of course, we can choose other materials for DFT calculation, but crystal structure becomes larger. Then we need to wait for a little bit better the supercomputing state system to apply the other materials. But that one is also very interesting. Maybe in the future, some of you, if some of you are interested in this kind of DFT calculation on other materials, that are very happy for me. Please think about such kind of possibilities. And this one is a general phase diagram of the high TC, Lancelot-based high TC cuprate. Important point is the high TC cuprate, Lancelot 2 kappa 04. This is completely ceramic, but this is an insulator. The insulator means not superconducting state and shows a magnetic state. It's a antiplanetary ordered long-range ordered state. The green area is an ordered state. So then once we dope the carrier, like electrons or holes, then we can see the superconducting state. That means the basic character is a magnetic material. So this is very important because the high TC superconducting state is on the basis of magnetic interaction. So that means that we have to discuss the magnetic interaction of these materials. Of course, there are many studies in the past on Lancelot 2 kappa 4, which is the complete mother materials for the Lancelot-based high TC cuprate. However, we still have more rooms to study by using DFT and also MSR. That was my viewpoint. So then, the reason why is high TC cuprate, especially on a coupled plane, the kappa's electric charge state 2 plus and has one electric magnetic moment. The electric magnetic moment, they has magnetic antiplanetary interaction each other like that. So then we need to discuss the static and dynamic properties of these localized kappa spins. How we can understand the magnetic properties of this kappa spin, that is completely key to discuss the high TC, the cuprate. Then the Mu DFT is one research tool for us to investigate more and more on the Lancelot 2 kappa 4. In some sense, our measurement is not like a major measurement, but we feel the missing knowledge on the high TC, the cuprate from viewpoint of MSR. This is the first measurement of MSR. Then this is my answer to the Professor Risty. We need a mu spin precision to discuss the DFT efforts. This one, the first observation of the antiplanetary ordered state in the Lancelot 2 kappa 4. This is a muon data. So we can see the cosine-like precision here. So this one is a coherent muon spin precision inside the material, inside Lancelot 2 kappa 4, on the basis of the long-range ordered state. Then the Fourier transform can show the single frequency like that. Then we use this kind of information. But this one is very fast measurement in 1987. At that time, the muon facilities were not in a good condition compared to the current one. Then I started my career to work on a muon science is 1987, from this year. Then at that time, I went to the Tsukuba high energy, the laboratory, the muon science, the laboratory. At that time, we have to wait for a couple of hours to get one muon data. But nowadays, we can use only 15 or 10 minutes to get the same quality data. So then this one's a very old data, but still very important and being still cited, because these are past data to show the appearance of long-range order state. So this mu spin precession is very important for our discussion. This is another example to show the different properties of the mu spin precession. This was obtained in the by using the thin film done by PSI. Okay, please see. First one, 1987. Second one, 2013. Okay, and still something is going 2014. Even after 20, 30 years, what we are doing is similar measurement, Lansan to kappa 4, Lansan to kappa 4. This is a quite good evidence why the basic study is very important, still important. So then I'm also trying to measure the Lansan to kappa 4. So this one is my old data to show the stripe state. Sometimes the stripe state, these holes, spins, shows a little bit interesting the formation like this. We say stripes. Then we found these stripes by using MUSR in the beginning. So then this one is my next target to apply the DFT calculations. At this moment, Lansan 2 kappa 4, this doesn't have any holes like carriers, but stripe state, this has carriers. Okay, so in order to add carriers in the DFT calculation, that is also quite hard due to the performance limitation of the computing facility. So then this one is a little bit simpler compared to the Dft one. So then we are now finishing the study on the LCO, the Lansan 2 kappa 4, and then trying to move to the stripe state. Interestingly, we can write down the stripe state like that, the unspecified order state spin alignment, but nobody has proved this spin alignment by using any experimental technique, just like a suggestion. Then my purpose is from DFT and MUSR, I'd like to confirm this spin alignment is true or not. Then MUSR is also very sensitive. For instance, if we change the carriers like that, the unspecified order state is changing by changing carriers. This one is Professor Adachi's the old data. Then MUSR can sense the change in the order state by changing the carriers. That means the stripe state is changing by changing the number of the carriers, of course. So then we can sense this kind of the change of spin structure from the stripe state by using MUSR. As long as we can see we can apply MUSR, and also as long as we can see this kind of mu spin precession, even from the stripe state, we can apply the DFT and we can discuss the electric state. That is important. Okay, so they come back to the fundamental problem MUSR. So if the position is unknown, if the position is the distance too far, Human interaction is very weak. That means the mu is not so easy to detect the information from the electrons, but very near, easy to detect, even though the origin of the electric moment is the same. Then again, the y is mu. Then we come back to the fundamental, the information. We cannot discuss at this moment anything from only experimental result. For instance, of course, there are many studies in the past on the Lansan 2 kappa 4 like this. So this one is the basic study to try to decide the muon positions in the Lansan 2 kappa 4 by using some different techniques. So then red ones are suggesting muon positions in the past. So completely scattered. So we cannot discuss which one is good and which one is better and which one is realistic. We cannot discuss anymore. The suggested points are completely scattered. Sometimes this is due to the limitation of the computing performance, and also sometimes the reason is on the basis of the bad assumptions to simulate the magnetic moment state. So then we improve all the conditions. Then they try to simulate the realistic electric state by using DFT. At the beginning, at the first stage, we simulate the muon positions by using a dipole-dipole induction. Dipole-dipole interaction is maybe you study this dipole-dipole interaction in the course. So then what we did is just we put just simple moment on the kappa. We say point moment. Point moment is the position is just only the atom, at the atom. But on the atom, we have the size of the mighty moment. Then dipolar field is coming from the kappa spin, from like that. Then we sum up the dipole field, covering the larger area to simulate. Then we judged the position to be true or not. But unfortunately, this result also cannot reproduce. The experimental result cannot reproduce all of the suggested positions, because this one was done by Budikun, who is in now UNPAD. So at that time, the computing resources were still good compared to the 20, 30 years ago. Then we can do the bigger estimation and calculations. Then we judged all of the suggested positions are not realistic. Then we think the dipole-dipole interaction only is not good enough to discuss a muon position, to realize, and also to realize the electric state of the magnetic moment. Definitely not good enough. Then we have to move on to DFT. So they are the next generation. The Professor Irwan and Professor Dr. Ramadan, they try to use the DFT calculations. So this is just a schematic flow of our techniques. So that we assume that we use a DFT, that means the density, the calculations. Then we assume the electric correlations among the density, the areas. So we say GGA PW91. This is one name, the name of the one electric correlations. So the GGA PW91 plus U, easy to write down like that, but very important to choose what's kind of the electric correlation function for our materials is a very, very the essence for DFT calculations. So this is how the density part are interacting together. The how interacting, that means how strongly, how weakly they interacting among the density areas. So then each electric correlation function has some kind of the correlation, I guess, a structure. Then the long range, short range, and how that is changing. So each electric correlation function specifies the type of the interactions. So what sort of type of the electric correlation function is suitable for our technique is very important. At this moment, GGA is very, very used for like ceramics and strongly correlated systems. But recently, GGA seems not to be so good enough. And there are some, one or two, the new electric correlation function that appear and suggested to be used. I showed one example. Then we have to move on to the next generations, the electric correlation functions by using our machines computing resources. But as long as the electric correlation function becomes new and becomes much more complicated, we need bigger computing resources. That is a problem. But anyway, GGA is very, very used for other strongly correlated functions. Then we said the GGA plus U. U means just like how electrons doesn't want to sit down together. Then electric structure, that means the potential calculation. Then from the potential calculation, we decided initial muon position as the minimal local potential positions. Then put the larger cells and put the 1 muon in. This is very important because if you use only one unit cell, then plus 1 muon, that is very unrealistic because each cell has 1 muon, which is impossible for realistic experimental condition. The muon is a very dilute, the impurity. That means we have to have the larger unit cell. Of course, if you can expand this unit cell much more larger, that is better. But for instance, even using a Hokusai, 4x4x2 takes 1 day or 2 days. Then if you can expand 4x4x4 unit cells, so that takes much longer, sometimes fail due to the memory flow over. Then we have to wait for the next generation, maybe that is coming in the next year. Then if some of you can join to me, maybe you can enjoy the much more better calculation condition. Then they put one mu into the larger unit cell. Then they simulate the local deformations and electric states. Then they self-consistently. Then in the end, we have to discuss and we have to compare with the mutual result and determine the muon positions and electric conditions inside the material. So then first, we have to specify the crystal structure. This is the basic information. Then the multi-moment like that. Luckily, Lantham 2 kappa 04 is very well studied by neutron scattering experiment as well. Then the antikinetic order state is very well recognized. But if you write down the multi-moment just like the arrow, they're easy to say, here multi-moment here. But this one is a schematic image of multi-moment. The how is a realistic condition of this multi-moment is a different problem. Then the DFT can reveal such kind of the realistic situation of the multi-moment. So then first we have to discuss the validity of the electric the equation function. So sometimes we cannot discuss, we cannot realize, we cannot reproduce a realistic electric state by using a long electric equation function. Then we have to tune the electric equation function to reproduce a realistic electric state. This is the energy scheme of each electric orbitals. And also this information can be obtained experimentally by the light application experiment. Then following the light irradiation experiment, we can determine how good, how bad our suggested electric equation function is. Then luckily our electric equation function, as proved in the past, that works very well for our studies. Then we decided also structure lattice parameters, and also some sort of the potential values to discuss the gap state as an insulator. So these are our basic information, starting information. So then on the next step, we calculated the electrostatic potential, inside the material. So then we wrote down just only this schematic view because the Lantham 2 kappa 04 is just like a block layer structure on the basis of this unit, the structure. Then we need to write down only this unit structure. Around this unit structure, then we can see some sort of local minimum potential positions like this, like a chair. Then inside here, we can have definitely the local minimum, the potential position. There are 3 positions like that. Then we name M1, M2, M3. So positions like that. So these are deepest position M1, M2, and M3. Then we start the self-consistent calculations. On the other hand, we have to measure the muon data, but the past muon data was not good enough to compare with the DFT calculation, because DFT calculation can give us a very exact value, but sometimes data cannot give us exact value. So then we synthesize a single crystal, the Lantham 2 kappa of single crystal on the basis of collaboration. So these are very high quality, the single crystal Lantham 2 kappa 4. The 2 types of samples we prepared, and we measured this type of samples by using the muons. And also on the basis of this data, we compare the DFT calculations. So this one, the real data, they obtained by the Buddy-kun a long time ago. Then if we apply Fourier transform, we can find 3 muon positions like that. So this one, the main peak was the measured in the beginning as the first data done by Professor Badnik 30 years ago. So this one is reconfirmed again, of course. But in addition to this, we can see the additional, the small component, the precision component like this, as M2, M3. So decided the internal field to be like that. So then the main peak is nearly the same from the beginning of the history of the ITC, but a little bit different because maybe this is due to the sample quality and also this due to the bad quality of the muon facility. But now we measured this one, the PSI, by using a very high, strong beam intensity, muon beam, and for taking a long time, and gathered like a 30 times bigger statistics compared to the usual data. Then we can say our data is the #1 data in the world. So then how to compare the experimental result and also the DFT result? That is the next step. So experimental result, we cannot change anymore because this is the experiment, the real nature, of the Lanson 2 kappa 4 with muons. Then we have to follow we have to modify, we have to improve or simulate the DFT side, following this experimental result. Then that is a little bit the problem sum. So for instance, as I said to you, the dipole-dipole interaction, this is very bad. So then these are experimental results. But if you apply the only dipole-dipole interaction, then simulate each muon positions, they are not so good. They are completely bad, like internal field nearly twice, nearly double. So that means the dipole-dipole interaction has overestimated. In order to realize, in order to reproduce a realistic condition of the multi-moments. For instance, the kappa 0.52 mu b, this was given from the neutron scattering experiment. But neutron scattering experiment can give us the total sum information of the distributed multi-moment. So how the multi-moment is distributed, neutron cannot give us. Only DFT can give us the information. Then by using 0.52 mu b, of course, if we can reduce this value to be in a half, like a 0.25 mu b, then we can simulate the MuSL data even by using a DFT. But 0.25 mu b is not allowed to give from the viewpoint of neutron scattering data. So then we have to use 0.5 mu b to discuss our data as well. That means the DFT and also dipole-dipole assumption is not so good enough. Very bad. So then what we did is that we set the supercell, very large cell, which can be just a maximum to be accepted for our Hawk side. Then put them only 1 muon because the density of the muon inside the material is very low. In extreme case, the muon, there is only 1 muon inside the material. Only one, okay, in the Avogadro number. So the muon problem is like a dilute spin problem inside the material. Then put the muon in, then simulate all the atomic positions and electrical state. So how many atoms, how many electrons, densities are there inside this supercell? This is a completely huge amount. For instance, we simulated nearly 1,000 atoms, nearly 1,000 atoms, 300 atoms, 500 atoms, or nearly sometimes 1,000 atoms, and the calculate the position of the electric state independently. This is the reason why we need a supercomputing state. So in 2003, there was a very interesting report on the muon. So this is just only a simulation, simple simulation with muon in the material. So if we put the muon in here, in the Lanson 2 kappa 4, the model is very small. In this case, this muon would push down the kappa position to the downside. That means the muon would deform the local spin, local crystal structure. This is the first report, first suggestion about the possibility of such kind of local deformation caused by muon. That means that we cannot ignore this kind of local deformation effect. Then, of course, DFT program can include this effect. So this is a simple result of the one layer, the crystal structure deformation. So if the muon put in just around here, then one kappa 2 layer is deformed. So this height of these bars are just how much deformed from the original position. The 0.1 angstrom, 0.2 angstrom is not so big, but still deformed. That means the muon can cause the local deformation. This one is automatically given if we can learn the DFT program with the appropriate condition. So this one much more schematic view, how much local deformation appeared is caused by the muon. The gray one, the black one, is the before and after the muon position after the self-consistent relaxation process. So after muon stopped in, muon comes into here, then push up the kappa multi-moment and deform the local structure of the oxygen like that. So if the muon stops here, muon move to this way, and pull up the oxygen to the downside and deform again the local structure. And if the muon stops here, move to this way and push up the kappa spin as well. So then the multi-moment is on the kappa spin. So if the kappa spin position is changed, what is expected is the deformation of the electronic state on multi-moment of kappa spin itself. So that has to be the monitored or simulated as well. So the VNI initial, AB initial, the simulation package program has this kind of the component to simulate the local deformation as well. So as long as you can exactly and correctly arrange the input files, you can simulate the local deformation and also local effect given by muons. These are the examples. So this is before and after the kappa spin distribution, the caused by the muon. Is the muon position here, kappa distribution here is deformed. So this is the density of the kappa spin formation. There you can see kappa atom here. Then the kappa atom is connecting to the nearest kappa in this direction. If so, the kappa spin density is expanding along to the this arm connection direction. Not yet this direction, not this side. So to the direction to the connection, the position. So the kappa spin density is no longer just like a point magnet like anymore. So then the kappa spin, the distribution is on the basis of the crystal structure and definitely distributed. So this defect has to be monitored by using the DFT. Unfortunately, we cannot sense this deformation by experimentally. The experimental method, muon, neutron, anything, they cannot provide this kind of the deformation of the kappa spin distribution. Then DFT has to be exactly done. That means that we need good resources and good programs to reproduce a realistic condition. Then we can compare with experimental data. This one, the next muon position, is on muon position here, the deformation becomes a little bit less because muon is too far from the kappa. On the other hand, if the muon sits here, which is very close to the kappa, the deformation becomes much more bigger. So this is very symmetry rectangular, but all the symmetry is already lost. So then we cannot discuss the symmetric electric distribution anymore if the muon is here. But please be aware, this one is a local deformation given by the one muon near the kappa. That means that if we move to the outside from this muon position, this deformation effect becomes much more less and smaller. That is also an interesting point. So this is a 3D schematic image of the deformation of the kappa spin distributions like that. So this is before and after. The kappa 1, 2, please see the muon spin here, muons here, like that. And also interesting point is here. Oxygen also deforms, like here. You can see here, like that. So that means a muon can deform the local structure and change in the kappa spin state. So this change in the kappa spin state has to be included to discuss with the experimental result. This one is very important and never been studied in the past. So then the next one is how we can simulate this kind of the kappa spin distribution. This is a local, I guess, a classic view of as a point dipole. It's a dipole-dipole field interaction. We set just only one dipole at the kappa position. However, this kappa spin is now has to be treated as just like a distribution, just like a density of the spins, like that. Then density around here, and mainly here and here. Then we have to include all of the spin densities to discuss the muon position, the internal field muon position. So then another point was suggested to be included to discuss the final result. That is the 0-point vibration motion. I think some of you know about this, but some of you don't know about this. So it's in the case of fine particle, which has a very light mass, the 0-point vibration energy becomes very big. This is due to the quantum mechanics. So if you are interested in, please just Google the name 0-point vibration motion. So that depends on the local potential structure. I talked to you in the beginning. We calculate the electrostatic potential structure. That is also important to discuss the 0-point vibration motion. That means the muon, we put the muon in the DFT calculations as a local point like that. But muon, realistically, in the realistic condition, muon cannot stable in only one position. That can be vibrating like this, following the local potential structure. So that means the electrostatic potential around the local minimum potential is very, very important to discuss the 0-point vibration motion for the muon. But this can be simulated by solving out the Schrödinger equation, and my student have developed how to solve out this as well by using a commercial-based program. So not so difficult, but we have to include this effect. So this one was suggested in the beginning by the Italian group in 2013 to discuss the muon positions in the semiconductor lithium fluoride and yttrium fluoride. So for instance, this one is the simulation of the potential, the potentials of lithium fluoride. So if they change this isosurface energy level to be like a 50, 100, 500 millieV from the very local, the minimum potential position, the area of the local minimum potential becomes wider and wider. But how do we think about 50, 100, 500 millieV? This level of the interaction has to be included or not? The answer is yes. For instance, in our case, Lansan 2 kappa 4, 0-point vibration energy is just in this level. So that means muon can run around this area. That means we cannot specify the muon position anymore. That means that we have to discuss the muon position as the area or as a volume. So then this one, the first suggestion to include the 0-point vibration motion. Then schematic view for the muon area is like this. So then we have to include the area as well. Then we calculated how widely the muon is vibrating due to the 0-point vibration motion. So then we can estimate like that. So this one is the resolution of the grid to calculate 0-point vibration motion area. So around just 1.5 angstrom, 1.5 angstrom for Lansan 2 kappa 4 for M1, the muon position 1 around here. This is not so small. This is not so small. Then we have to take into account each grid position to discuss the hyperfine interaction. So that means we have to include two components: the distribution of spin effect, the distribution of spins, and also 0-point vibration motion. So both effects have to be included to discuss the final result. So this one is the first trial in the real world in the past. So then we try to carefully to discuss, but not so easy to publish because there are many steps to get the final result. But if we include the 0-point vibration motion and spin distributions, we succeeded to reproduce the experimental result from the DFT calculations. Then to optimize the DFT calculation conditions, then we can find out the final electric state from DFT calculation. That is the view of the distribution. That is the final, very new result obtained from our recent calculations. Okay, so this is one way to apply our DFT for MIRSA result to discuss the electric state. So then the reason why we are now doing is this DFT calculation is very important nowadays for muon people. For instance, this one is like a memorial, the published paper in 2013 to celebrate the ICES, like a Rutherford muon facility for 25 years old. So in here, we contributed the one paper to discuss the muon spin positions with other collaborators. So Bernardini, he suggested 0-point vibration motion. Mueller is a Oxford University student, but he's been to the bank area at this moment. Steve Brander, he's a top class, the professor in Oxford University. He's leading the activity, muon side calculation activity in the UK. The Drenzi, he's also the professional to do the MSR and also muon side calculation in Italy. So these are the leading this kind of DFT calculation in the world. Sometimes we meet together and discuss the recent progress and discuss and compete each other. My target is high TC, their target is not high TC lucky. Then we can sometimes collaborate and give and take the new information, then to improve our own calculation. For instance, one example is this one is the lithium fluoride. This is Oxford University study. They calculate basic potential and muon area like this. So then the muon area is very, very wider in the cobalt fluoride and calcium fluoride, lithium fluoride. Then they suggested to think about these kind of the larger area to discuss the muon positions. And also this one is a lanthanum cobalt phosphide, and decided by suggested by my collaborator in Malaysia, Professor Shukri Sulaiman. The muon position is like this, but this method is a little bit different. We use a DFT. He uses the DFT as well, but package program is different. Our package program is BUS. BUS is on the basis of the plane wave method. They use Gaussian. Gaussian is like a molecular-like, taking into account all the electric orbitals. We don't take into account the electric orbitals. We include, we arrange the electric orbital to be just like a density. So then the Gaussian cannot treat the larger cell, but DFT, the BUS can treat the larger cells, which is much more better for muons. This is another example of the DFT done by PSI, the Switzerland group. So for the lanthanum, the ion, the high TC superconductor. So muon area is like this, and like this, and like this. Then we have to discuss the muon positions, not like a positions anymore, just like areas of volumes. This one is another example done by the Italian group. This one muon positions on the graphene, one seed. They measure the MSR on the graphene seed and measure the hyperfine interactions on the muon side. So how muon is attached to graphene is also very important to discuss the graphene, the electric state. So then by using MSR, we can discuss many things, but we need DFT to get the further information of the electric state from materials. So we cannot solve the MSR just only by experiment, but we need to discuss the DFT as well, which is not so easy for experimentalists. The collaboration with the DFT guys, or we have to do by ourselves, is just like a next step, next generation research style for MSR. This one is typical, and also as long as I understand, maybe only one example to show the successful achievement done by Oxford, the group. They discussed the Gaussian-like the property by using a DFT, decide the muon position, and do the DFT calculations and simulate how the Gaussian properties can be explained. This seems to be successful, but a little bit questionable, because we discussed with their group, especially Sean Gibbon, he's a leader, one of the leaders, but muon position is not true for our viewpoint. Then we send a question many times to Sean Gibbon. This one is a long point. They're on the basis of our knowledge, but they didn't reply to us so much. Maybe this one is a quite beautiful result, but maybe they're questionable. Then this one is we have to resimulate again in the future. This one is also one good example why the DFT is very important even for high TC now. This one is published in 2000, very recent, 2018, I think. They are done by the DFT group. Their group is a very special for DFT only. but they are still calculating, estimating Ransom 2 kappa 4. Okay, Ransom 2 kappa 4 was found 30 years ago, but still DFT people are interested in. So that means that they are trying to simulate the crystal structure and electric state by changing the electric correlation function. Especially this scan is a very recent the electric correlation function to be examined. So their group is just like a developer of the scan function. Then the Nature family paper compared with this recent the electric correlation function with all PBE and LSTA the electric correlation function, and appears this function is the best function at this moment to reproduce electric state of the strongly correlated system. So our plan is to simulate the scan, simulate reproduce our data again by using a scan. So one guy in the Defense University, he is my old student, the Dr. Ledo Ramadan. He is now doing to reproduce our result by using a scan and others. So then if you're interested in, please contact with the Dr. Ledo Ramadan in the Defense University, and also the Dr. Ilvan, Professor Ilvan. He can give you the good suggestion how to carry out, how to join to DFT, the calculation activities. So then this one, the most recent one, 2018, okay, Ransom 2 kappa 4 again. So that means still we need a DFT to discuss Ransom 2 kappa 4. Then they apply the scan, the electric correlation function to reproduce the electric state exactly. So then how we can use this scan could be the next problem for us. But scan is quite a complicated function, so then they're not so easy to apply with MSR. Then I have to wait for the next generation of supercomputing state in Riken. But from next year, we start to use the scan. Or this year, we have to use the scan function to discuss the materials. Okay, so this is our past studies and my plan. But how we can apply the MSR with DFT I'm not suggesting to work on the battery and the solar cell materials by using MSR and DFT. For instance, Professor Risdi from UNPAD is now working on the MSR with the solar cell materials. And now the battery material development is very key, important point for Indonesia. So Indonesia government is now very keen to encourage all of you to work on the battery materials. Then the battery materials is also very important. Luckily, there are some people, MSR guys, who are now working on the battery materials by using muons in order to investigate the lithium motions by using muon. But they need the help of the DFT. So then I can suggest to work on the battery materials. So this is a very important research themes for the Indonesian future. So you are the person who can work on the research fields. So especially Indonesia is a quite good country to produce the original materials for batteries. But unfortunately, you have no knowledge, not so much knowledge, not so much technique to make the real battery products. But you have mother materials like iron sand and phosphides within the country. So why don't you have the research, the efforts or research techniques to produce the real productions from those materials within the country? That is my suggestion. Then from viewpoint experiment, I'm now suggesting some research collaborations with my friend in the UK. He's in Sika this moment, so that we cannot work with him so much. But there are many Indonesian people who are interested in battery materials. So why don't you form research teams on the battery by using muons, DFTs, and others? I'm very willing to collaborate with all of you. Then I can suggest together. I have some friends and the collaborators in the Palopo and ETS, Surabaya, Lipi, the Depok, and also Malaysia. So then the Malaysia, USM, Penang. So then we can collaborate together then to develop the research techniques and knowledge and materials for batteries. So then you can support your own country's future. So that is my suggestion. Then if you're interested in the DFTs or MUSR at any time, please contact me. Then I'm very willing to talk with all of you. Then Reckon has a system to accept some students, especially PhD student. Then if you are interested in, then if you can join to us, at this moment, the couple of students are still working with me in Reckon. Then please contact those students as well, how good, how bad the Reckon is. Then if you're interested in, at any time, please contact me. So just a 15 minutes we have to go, then I can discuss with you the question and comments. Thank you very much. Terima kasih.
Okay, thank you very much. A very nice lecture today. So if you have any question or comment, please raise your hand. Or okay, we already have one question. Sorry. Okay, one question from Eka. Uh, Thank you, Dr. Watanabe. I have a question. If the input of one particle is not available in the DFT calculation, it means that we have to approach the input that is close to the experimental result, so that muon are validated as a point particle, such as positron, or muon as a hydrogen atom.
Yes, the concept is very true. So then we are treating the muon as like light elements, like light hydrogen. That means that inject the muon is just similar to inject the proton into the material. So then in some sense, this is muon problem is always a dilute impurity problem with magnetic spins. So that causes a DFT calculation heavier and bigger. Is it okay to your question?
Yeah. Eka, is it okay? Eka, okay.
Okay, Prof. Disdi dan Dr. Watanabe, thank you.
Okay, okay, thank you, Eka. Any question or comment? So, okay, we still have 10 minutes or 15 minutes. Any question or a comment? Okay.
Prof. Risdi, may I have question?
Okay, Suji, please.
Hello, Watanabe-san.
Hello, Suchi-san, how are you?
Good, and you?
Good. A little bit tired.
Tired.
Yeah, a little bit tired, yes.
Okay, so thank you for your presentation. I have two questions. Is it okay?
Hi, hi.
So the first one, after we know the muon stopping position, and then how we can analyze electronic structure or electronic interaction of the system. I think it is not yet announced in your presentation. And then the second one, if I'm not mistaken, you told us the stripe theory in high TC superconductor is not proved yet at this moment by any computational theory. So my question is, what is the problem actually that we need to tackle off or we need to consider when we calculate stripe by using the FT?
For the first question, from experimental viewpoint, it's impossible to discuss the detailed structure of the kappa spin state from MUSR. It's impossible because the mu has the area to stop, like a 0-point vibration motion, and also kappa spin itself has the distributions. Then the MUSR result is just like gathered information. It's average information. So then we can see the average information, but we cannot see the detail. So that is a fundamental problem. That is why we need the DFT calculations. And also, in the past, there are many trials they have been done to discuss a MUSR result, but almost of them are failed. As long as I know, just only one example was succeeded, done by Francis. But that is a very dilute, the organic systems, but others completely failed. So the reason why is mu has a fundamental problem to, like, how can I say, resolution or the space resolution. The mu c always average the information. That is the one problem. Then we need a DFT the support to discuss in detail. So to the second question, the stripe, the problem is how we can realize the doping level in the DFT calculations. The lanthanum 2 kappa 4, there is no carrier. The stoichiometry of the crystal is very easy. But for stripe, we have to replace the lanthanum to be strontium. If so, how much the lanthanum we can replace in the DFT computational model? That is the problem. So if we replace just only simple one in the units from the unit cell, just replace one atom, lanthanum to be a strontium in one unit cell, that makes a lanthanum strontium kappa 4. But it's not a stripe. It's a 50% doping. But we need 11% doping. That means we have to replace only one lanthanum from the 8th cell. Okay, 8th cell. So already 8 cells, they're 4 by 2. But in order to put the mu in, we need a much larger cell. That means we have to build up this kind of 8 cells. That makes a much larger the supercell. Maybe not only 4 by 4 by 2, maybe a little bit bigger. So at this moment, I don't know how much the Hokusai can accept such kind of big cell. That is a machine problem. Maybe next year could be a possibility. Could be a possibility to us to try that kind, because BW, big wave, the big waterfall system is being replaced to be a new system next year. So maybe much more better system is coming in to reckon. Well, so that is the next question.
So it means the more complicated our crystal structure that we have, so the more complicated the computational. Is it?
Not more complicated, more heavier. Heavier calculation. That is the problem. And also the stripe state, the first data given by neutron was very shocking. Very, very shocking. Then everybody said, oh, stripe was like that, stripe was like that. So then they forget to investigate how the stripe is realistically to be formed. So then some people said, not like a same spin, the 3 aligns, just like sometimes waving like. But nobody has investigated because a neutron doesn't have such kind of the resolution, nothing. So if you see, come back to the Tranquilla first paper, the Tranquilla clearly said, this is a model. If we assume this model, we can explain the experimental data. So then what is an exact stripe state is the question. And also after that, we discuss a dynamic stripe or deformed stripe. There are many stripes out there. So then how much we can reproduce those kind of stripes. We discuss. However, we have no real data to show the exact spin alignment. That is my motivation. Why I want to try the DFT on the stripe.
Okay.
It's okay.
Okay. May I have one more?
Hi.
How about the sample? I mean, to perform the Dft calculation, should we have single crystal only, or we can have thin film or polycrystal or any material?
As long as the quality is good, anything is fine. But thin film is not so good. Because the thin film sometimes has the crystal deformation, which is coming from the attaching point to the substrate. That was proved by the PSA guys. Not so good. So maybe polycrystalline or hopefully single crystalline, because single crystalline is much more better quality at this moment. And also how to synthesize a single crystal is completely established at this moment.
Okay, thank you, Watanabe-san.
Okay. Okay, any other question or comment about anything? Mas Irwan, do you have a comment? Or Budi? We have also Michael here.
Yeah, I have question. Can I have question, Watanabe-san?
Okay, please. Okay.
Thank you. Excellent talk. Thank you, Watanabe-san. Yeah. Hi. I have at least two questions. First is the I saw that your in DFT calculation there's a like potential electrostatic potential, right? There's a in the picture. Can we use instead of I mean that's from DFT calculation. Can we use direct from like electron density distribution from X-ray or probably neutron density distribution from neutron diffraction?
Not so easy.
Not so easy.
Due to resolution, because
Yeah.
X-ray has a limitation of the resolution due to the wavelengths. But wavelength is very similar to the crystal cell. So that means my saying distribution is within the cell. So not so easy.
Not so easy, yeah. Okay, the second question is about interest about there's a deformation about the position, right? Is it any like idea to combine with in situ something like neutron or X-ray diffraction when you measure using the muon, so we can see how much actually is it where is the, as you can see we can let's say single crystal, we can check the it's really happen the deformation on when the muon side go into the site as you predict.
Yes, technically it's not impossible. Technically it's not impossible, but the problem is the density of the muon is too small to be detected. That is a fundamental question. For instance, in PSI, only one muon in one material. Or one muon against the Avogadro number. So then even though we apply the X-ray or something at in situ condition, we cannot detect anything.
Okay, thank you very much. Thank you very much. Excellent. Thank you.
Okay, thank you, Dr. Michael. Any question or comment? Okay, we still have 5 minutes. Budi or Irwan, do you have a question? Comment? Okay. Oh yeah. Okay, Irwan's already there. Yes, please, Mas Irwan. Yeah.
No, I don't have comment, Professor Lisdi.
Okay, it's no problem. Just say hello, see your faces, so it's okay. Okay.
No, he's got my pressure. Yeah, he's having my pressure.
Okay, Budi, would have question or other student?
Maybe I have one question.
Okay.
I'm outside the house. Is it okay?
Oh, it's okay, no problem.
Okay.
To be honest, I really interested to Suchi result about LCO that nanostructure dependent. So I'm curiosity about how to reconstruct the spectrum in those materials. But the problem is maybe the computer power in Indonesia is very limited. So my question is it possible that I have another channel to use the Riken cluster, the Hokusai, to calculate it?
Yes, of course, that is very possible. Then, but unfortunately, that is not free anymore, free of charge.
Oh, not free?
Not free of charge anymore from this year.
Oh.
We have to pay. So, but at this moment, I've got a grant for next 3 years. Then as long as we can, I can say, make a team it's possible.
Oh, okay.
And my team head is Professor Shukri Salaman in Penang. Then if you have, I'm also thinking about how to simulate the Suchi-san data. At this moment, how can I say, boundary condition is a problem for me. How we can make a boundary condition in DFT calculations because Suchi-san case is nanostructure. How we can include a nanostructure into the DFT, I have no idea at this moment. But there is a paper to discuss this point. So then maybe he's a Japanese, so at some stage, I can discuss with him how we can simulate the nanostructure for LCO. That is also very important as a next step.
Okay.
So if you're interested, please discuss with Suchi-san. Just she is beside you, I think, in the same laboratory. So then she knows about Suchi-san なんかheavy fermions nanoparticle paper, including the theory calculations. Do you remember it?
Okay.
Heavy fermion.
Heavy fermion. You gave me heavy fermions nanoparticle. Then there is a simulation, theoretical simulation there. Then the skin effect.
Yeah. Okay, I will give the paper to Budi-san.
As long as I understand, that is only the paper to discuss from the theoretical viewpoint.
Okay. Thank you. I will wait for the paper.
Okay.
Thank you. I hope I can again the Hyokisai cluster because it's really struggling in here to find the computer cluster.
So that will be much better next year, I hope.
Okay.
Okay.
Thank you.
Okay. Thank you, Budi. So another question from Fikri from ITB. So dear Dr. Watanabe, in the correlated material, do the choice of U value, potential value, affects the muon size?
Oh, very good question. I have no idea how to answer. So at this moment, I'm now thinking, following our research, DFT studies, this has to be the muon position should be affected by U. So the potential value. So that is my image at this moment. But at this moment, I have no way how we can prove it. On the other hand, this is the U value. It has to be included as long as we stick with the GGA, the electric equation function. But if we do the scan, we don't need to include the U value. If so, how do we think about the U in the DFT? That is a fundamental question. Unfortunately, scan is too new at this moment, so not so many people are using the scan. So then, if you are interested in, you can download the maybe scan. Then you can enjoy, like even using the quantum espresso. At this moment, I don't know how the scan is being used, should be used for our calculation. I'm not asking the Ramadan to test the scan, the electric equation function.
Okay.
Maybe I will try to examine that one with my new student in this year.
Okay. Okay, thank you very much for the question. Just a last question about our next project. So last week we already submitted our proposal for battery, isn't it? Could you please just briefly explain what we are planning for the next years?
Just I applied, but I don't know whether we can get the money or not. If we can have money, what is the question is that is the materials informatics. That means that we have to gather knowledge on the DFT calculation of the battery materials. Because DFT on the battery materials is also very important because battery, inside the battery, the ions, like a lithium ion, sodium ions, should be moving around. The ion is moving, okay? Local deformation is happening. It's like ion comes in, local deformation there, and again there.
Yeah.
So that causes like a problem of the battery quality. So how much we can improve, especially by using your own materials. For instance, if you import the mother material from Indonesia, then qualify the mother materials, then we can synthesize the batteries in Japan or somewhere with, of course, highest quality. But very expensive, even for us, very expensive. Then you have to re-import again from Japan to Indonesia with a car or something. That's not so good. That means Indonesia has to wait for the development from outside the countries. But unfortunately, the development performance in Indonesia is not so good. Then I have two ways. One way, I applied the another way in this summertime. One way is to how to qualify the material by experimental techniques. The another one is how to qualify the material, and also how to develop the material by using your own mother materials. So that is important. For instance, the Darwinson said, in Surabaya, they can have like an iron phosphide or something. Then they are now trying to synthesize the well-known materials, but the quality is not so good, of course. But even using a not so good high quality, you can make a battery. Like a LiPi, in a LiPi, they already produce some batteries, simple batteries, like a motorbike. That's also good enough. How to improve the quality and performance, you need a knowledge of the how to qualify by experiment, how to design by the DFT. But this moment, I have, maybe I don't see any people who are working on the DFT to qualify the battery materials in Indonesia. So at that point, I'd like to grow up. So that is the main point of my grant, the suggestion. So once we can have the grant, I'd like to ask you to nominate or to specify a couple of students to work on this. Then maybe you can also have some money, then you can employ students. If I have money, you can also have automatically money. Then I can invite the DFT specialists there to discuss with some of you to encourage. The first year to investigate what is the past investigation of the studies on the DFT. That means the desk work's very important. So you, a couple of students, they can work all the day, investigate. Then they gather the knowledge. From next year, in parallel, we set up your own account in the Hokusai. Then we can support the cost. Then they start to something from next year. That is my general idea. I don't know whether it's accepted or not.
Okay. Hopefully, our proposal will be the funding will be granted for the.
Please pray for all of us.
Okay, of course. Yeah. Okay. Okay. I think the time is already up. It's already 2 hours. Very nice talk. Very nice lecture. Before we close the lecture, we have a photo session. Could you please open your camera? So, okay. Okay, thank you, Wilman. Okay, great. So this is for our first slide. Sorry. Okay. Sorry. So, just a moment. Okay, Eka, Nur Hanifa. This is the first slide. Okay, Eka is already okay. First slide is already here. Okay, 1, 2, 3. Okay, just a moment. Just I just want to copy to the slide so we can directly. Okay, just another picture for the first slide. 1, 2. Okay, thank you. This is for the second slide. Okay, the second slide. Okay, Helma, Trijoko, Nur Anissa Trijoko. Okay, Nur Hanifa also already here. Okay, 1, 2, 3. Okay, another. Just a minute for another picture. 1, 2, 3. Okay. 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 Thank you very much. Okay. Okay. Thank you very much for Dr. Watanabe for very nice talk. I think all the students are really really happy to get the lecture, get information. Twice lecture from you. It's a very valuable for us. Hopefully we can get the next lecture for you in the next semester. Again, thank you also for all students, for all attendants, for from Pertahanan University, from Palopo, from ITB, and another university also for all the lecture from Unpad, Pak Togar also here, and Pak Andri, Pak Budi, Suci, and all students. Watanabe-san, again, thank you very much for your time, for your lecture, for your nice talk. Please give a big applause to
You're welcome. You're welcome.
Thank you very much.
It's my
Okay.
great pleasure.
Okay, we close our lecture today with Alhamdulillahirabbil alamin. Assalamualaikum warahmatullahi wabarakatuh. Thank you very much. See you.
Thank you very much, Watanabe-san.
Bye, sayonara.
Bye.
Thank you
very much, Dr. Watanabe. Bye-bye.
Sayonara. Bye-bye.
Terima kasih.